Okay, so we'll proceed on much awaited shadow acne. So we'll add slides for it. Okay, so as per the discussion, shadow acne is something like whatever the undesirable, the lining what we receive. So I think I have, or I can show it. I can, so we don't need it, so we will kind of comment it. Okay, so shadow acne is visible, and as light comes flat to it, then okay, so this is shadow acne, and it is different on this table and on this yellow plane, so that is visible. So same thing what we can see here. Shadow acne generated while drawing the shadow, and acne width is proportional to the angle between light source and shadow normal. Okay, so if this is light source and this is shadow normal, so this is normal, so shadow is being drawn on this surface and shadow is being drawn on this yellow surface. So this red color what we see the mark, so this is normal from the yellow surface, and this red color whatever we see the mark, that is normal from the table. So whatever the light we are receiving, so this vector, the yellow color what we see, so this angle, I think angle is prominent, so this angle, so if this angle is more, then acne will be bigger. If this angle is less, that we can see it is less, so this acne will be smaller. So this is what is been seen. Okay, I think we can see that. So we will kind of change -10 back to 0. So it will be above only, and then we will try. Okay, so if I bring it down, it will be bigger, that we can see. Okay, so if light is falling on a surface and the angle between light and the surface normal is high, then this acne will be bigger, and if it is falling on this yellow surface, then normal is, and this light falling, the angle is very less. So we can see that acne is, the distance is less. Okay. Okay, now we'll understand the mathematics. So if we see the code, so there is a final pass in the code. Okay, so first we generate the texture. So first pass we generate the texture, and in the final pass, from the same light source location, we see the kind of the surfaces again, and then we receive kind of 3 coordinates per pixel, x, y and z. So x kind of x and y -1 to 1 range we get, that we slowly we transform into 0 and 1, and whatever z we receive, so that is the depth. Okay, now with x and y, what we receive in the second pass, that is kind of indexed into the shadow texture that we receive in the first pass. So it will come to xy coordinate where it is, and whatever value we receive, that is the depth. So that value will be compared against whatever we saved in the texture. So that is the idea. Now, like if I have a kind of model view matrix, that is identity, then I say GLU look at. So we modify the model view matrix, and then we add the bias to convert -1, 1 to 0, 1, and then we change the shadow matrix in the shader code. So if we see the shader code vertex, then we have kind of shadow matrix, that is the kind of projection matrix and multiplication of the bias, projection matrix and model view matrix. And then model view matrix what we draw. So and then what is the vertex. So if we combine all three, so if I call at the end draw, and then if I see the function draw, then we do lot of translation. So this would change the model view matrix. So first shadow matrix, so if I see the vertex shader, then shadow matrix, so shadow matrix is nothing but initial projection matrix, bias and model view that is received from the GLU look at. So that is it. And then whatever, while drawing, whatever the translation and rotation we do, and the GL vertex. So this is the vertex that is kind of, we think if the model is kind of kept at the center. So model is kept at the center, and then whatever GL rotate and translate we do in the draw, and then whatever the projection and translation we do through the GLU look at. So all three kind of we multiply to get the depth projection. So depth projection x and y. So depth projection x and y would kind of map into the texture buffer. So then we'll come to a conclusion that which point it is pointing in the texture buffer, and then the z depth. So depth is kind of it is finalized. I mean, if there is a battle, then there is a finalization. So depth is finalized. So depth is finalized in a kind of, so we see, so depth projection. Okay, so this is not the equation, I believe it is wrong. Okay, so shadow coordinate dot z, so depth projection dot z, so we'll modify it. Okay, so we'll add dot z. Okay, so we will add dot z. I hope it would nicely fit in, or I'm going to shift it. Okay, so I saved it. Okay, so whatever the ST, so depth projection ST, X and Y, we map into the texture 2D, and then we receive some data, and then we compare with the depth projection Z, and if the item, so it is like whatever, so okay, so these are the data that is found in the texture map. So that is this. that is this, and then whatever we receive in the final pass. So in the texture making pass we get the texture, and final pass with the XY coordinate we try to see the data. So if the data is bigger, in the sense that if this is the model that is the nearest for this pixel, and then we are drawing somewhere here, okay, then this Z from the light source is higher to the Z depth that this sphere enjoys. So if that is the case, so if texture is less than this, means if this project is higher, then it is shadow, otherwise it is not shadow. So whatever color we are receiving, so that color will be faded. So that is kind of analogy we are using. Now if we go to kind of in depth, now every kind of model, so generally it will have some primitive to draw it. So if I am using primitive GL triangles, then model is a set of GL triangles, means there are many GL triangles. Okay, so there can be many GL triangles. So if I take a sphere, then in the sphere there are many GL triangles. So one is Mr. Triangle this. So it is made of GL triangles. Okay, so it is like this. Okay, so this is like this. I mean, I can keep it somewhere. I can keep it here only. Okay, so this is like this. So one triangle I am taking. So this is how we make the model. So it's a kind of series or it's a kind of mesh of triangle. So one triangle I am taking. So inside one triangle it is set of pixels. So this is the kind of in the second pass. So second pass there are two things. If I see the source code, okay, if I see the source code, then there are two things. So this is first pass. So first pass is passed. In second pass, we kind of we do all the multiplication and we update the shadow matrix in the shader, but we don't draw it. And then we set the texture map, and then we set cam matrix, and then we draw it. So if I see the shader, okay, so vertex shader, then in vertex shader there are two matrices, cam matrix. So in a final pass the cam matrix is the actual camera matrix and shadow matrix is the light matrix. Okay, so there are two matrices. So GL position of the pixel is the camera matrix and depth projection we are receiving. So when we see any texture, then we do texture 2D. So texture map is the actual texture, and this is the XY coordinate that we place inside the texture 2D to fetch its value at that location. So in this picture the kind of texture sampler, okay, so texture unit. So texture unit is a guy, please refer OpenGL texture tutorial video. So texture unit is kind of it's an entity which refers to a texture object, and based upon the ST coordinate it fetches the texel. So texel is nothing but depth texture, so depth value, so that we receive. So that is the idea. Okay, now in the triangle, so whatever triangle we see on the sphere, So it has set of pixels. Now if we see the texture generated, then same triangle we can place, but these are the green colors are texel, whereas these yellow color are pixel. There are two things, pixel on the screen and texel what we see in the texture. So density or resolution of texel and pixel, certainly it will be different. Okay, I mean I can do lot of mathematics to make it same, but it can be different. Now if I merge these two, then in the second pass when from the light we try to get these values. So like I am drawing a pixel on the surface, that red color pixel, then that xy or st coordinate would map inside the texture, and then finally we received the depth value. Okay, so when we talk about in the texture map, when we kind of map the xy value, so that is the texel coordinate, so that is between 0 and 1. So it would map these three texel coordinates, some arbitrary, one texel coordinate in the xy direction, other texel coordinate in the three corner, and other. So in the second pass, whatever we are drawing, so that would map in the texture at the three corner, and then we bring the kind of bunch of pixel inside that, and then other texels. It would not match. Okay, so pixel density is higher and texel density is low in our case. I mean other cases that we can think. So shadow width and shadow height is 256 by 256 pixel, whereas we take 800 and 600 in the same area. So this is the big window we have taken. I mean mathematics may not be related, but this is how it is. So the density would not be same. Now if we see the kind of a texture and pixel mapping, so that comes under MAN and MIG, so minification and magnification filter. So here it would be magnification because the texel density is less. We choose the nearest. So pixel, so there are a lot of pixels. So each pixel value for the coloring. So when we go from vertex shader to fragment shader, so vertex shader is talking about okay, so kind of three vertex. So it has three vertices. So this is not I have drawn. So but I can show it. Okay, so if we see the kind of vertex shader, then cam matrix is GL position. So for a particular kind of drawing model, or we can say drawing primitive, for GL triangles, three positions would come. Okay, and as per the three position, depth projection also will have three positions. So this depth projection is nothing but texture coordinate, but this GL position will be the pixel coordinate that I have not drawn. So whatever I am showing, so this is the texel coordinate. So texel coordinate would map inside the texture, actual texture, and then it will map the three texels. Okay, so now inside that three texel, because of Mr. Cam matrix GL position, the three vertices, so it will now get the actual pixel inside it. Now pixel and green color is texel, so pixel texel relationship will start happening. Now we are saying the min filter or mag filter. So here it is mag filter. So lot of pixel would map to one texel and it is the nearest. So I can say I have put in a circle. So these many pixel would now, they would kind of refer to the same texel and it is nearest. And if it is nearest and they refer to same texel, then the pixel which are the depth of the pixel which is greater than the texel. So right side if I see, then the depth would be greater. Left side depth would be less. If it is less, then it is bright, and if it is right side, then it is dark. This is what we are saying. So what is the problem? Inside the same triangle, there are so many triangles. okay, if I see the sphere, then there are so many triangles. In each triangle, at each text cell, there is a region where it is white, there is a region where it is black, and now, so this is for this text cell. If I talk about this text cell, then again left side is bright, right side is dark. So inside a triangle, we see white, black, white, black. So light and shadow we are seeing inside the same triangles. So if this is the shadow, if this is the surface, then we are seeing white, black, white, white, black, white, black. Means in miniature science, if we understand textile pixel, then inside the same triangle, I mean GL triangles what we see, at each text cell we are seeing white and light and shadow. So this is the problem. Means, so even if I increase the density of the text cell, it would not match per pixel wise. I mean, I cannot go for that kind of mathematics. Okay. I mean, if someone is good at mathematics, then he can try mapping pixel and text cell. And then, so interpolation happens. This is what I was trying to say. So, if kind of, if I know the depth at these vertices, then this pixel depth, so many pixels are there. So this pixel depth would be interpolated, and that interpolated would be not the same as this text cell. So there is a problem. Okay. So this problem can be because of we use nearest, we can use linear. This problem can be because of the image what we take is less density. We can make 512, 1024, 2048. Okay. So in those cases it would differ. Okay, anyway, screen pixel resolution I can't change. I mean, we can do some mathematics to make it kind of abstraction change. So that can be done. Okay, I believe through kind of depth reshape. So viewport width and height would do some magic. Okay, so I would now draw it, and something I'll try to change. Okay, so this is the beginning. I mean, this is crystal clear. So let's see if beginning is changing. So this is the beginning, and then I am going to, so nearest I'll make it. Okay, so as I say, everything is crystal easy in Python. So commenting is also very easy. So GL nearest, I can say it as linear. Okay, let's see if really changes. Okay, I would say it's different. It's certainly different. Now, if we see the acne pattern, then they are different. I mean, which is left, which is right, I don't remember. But it is different. Even shadow is different. Okay, so I believe this is the nearest because we can see lot of differences are there. With a linear, it is smoother, but problem is there with both model, linear or nearest. So that is not the solution. Okay, I am going to delete this and revert back. Okay, so okay, now I am going to change the texture size. Yes, comments, just put hash and amazing 1024 and 1024. So I am making it big. I believe 4 times bigger. Let's see if it is changing. It is different. Can we see? Again difference. Now acne is smoother. Here it is coarse in 256, but the shadow is gone for toss. Okay, so we can see. Okay, so here it is better. Okay, again we have to think about so many a permutation and combination. Okay, but anyway, we'll revert back to 256. No need to do too much, no need to apply too much brain. Okay, so now we understand why it is kind of continuous black and white. What is the solution? So solution is whatever the pixel that is on right side of the text cell and that is coming under the GL near of the, because beyond this it would come under this text cell and this text cell. So whatever this text cell is covering, so that region, if it is in right side, then we will we will subtract with some delta, okay, some delta distance, and so that this text cell, these pixels would appear on the left. So if this pixel is delta x on the right side of this text cell, I will decrement delta x so that it would appear at the pixel or left side. So whatever we see on the right side, so it should go on the left side. If it goes on the left side, then it will be completely white. So again, for this text cell, whatever comes on the right side, full right side we will shift in the left side. But what is kind of other way of consequence? Then the image would shift, shadow would shift, because text cell by text cell we are shifting like this. Slight shift will be there in the shadow and the image. Means this is the downside. Okay. Now how much is the delta distance we have to think. Now let's see the kind of projection analogy. Now if I see the projection, okay, so depth, reshape. So if I see the projection, we have used GLU perspective. Consider I am using GL ortho. If it is GL ortho, then the distribution in the depth wise it is kind of consistent. So now if it is kind of near plane and if it is the far plane and L is the distance, then we normalize L to 1, because this is what we have seen, that 1 is the maximum distance that we see in the texture. But why this is 1? Because when we create the texture, at that time we set it as GL float. If I set unsigned int, it will be bigger. Okay, so we set as GL float. We set GL float. Okay, so if we set GL float while loading the image as GL depth component, then in the format, then it would be maximum 1. So 0 to 1 it would normalize. Okay, so that is the concept. So whatever the distance near and far we are taking, that we have to normalize it to 1. Means it will be normalized. Now, okay, so if we see this diagram, the kind of we have seen, we have taken kind of in ortho, it's a frustum. Okay, so it's a frustum. So if I see the frustum, then this is the far plane on which the shadow would appear, and this is the surface. Suppose in this on the surface, that is a sphere, any point is at distance L1 from the light source, and any point on the surface where the shadow would come is L2, and total distance is 1. Okay, so L2 and L1 from the light. So in the frustum, now I need to normalize L1 and L2. That would be L1 by far minus near, L2 far minus near. Consider far minus near is 300 and we have taken 300. Okay, so we have taken 300, 1 to 300. Or if I had done GL ortho, it would have been 1 to 300, means it was 300 everywhere. So far minus near is 300, and light, suppose that kind of, okay, so this light source is kept minus 100 in the Z direction. It is at minus 100. Okay, so that is not the case. Light source is at minus 20 in our example. Okay, suppose it is minus 100. Now L1 is at minus 40 and L2 is minus 2. Now if I normalize L1, it is 60. Minus 40 means it is at distance 60 from the light. So 60 by 300, it will 0.2, and then L2 will be 0.266. So the distance between surface and model and the surface on which the shadow would be drawn, so that would be this minus this, that would come as 0.66. So if gap is 20, then the distance, normalized distance is 0.6. But in practical sense, this triangle will be very small. Okay, so it will be much smaller than 0.6. But this is the analogy. We are talking about interpixel distance, so that finally we will come to this delta distance from the texel to the end of the pixel, what it covers. Then this is how, if this pixel, the third pixel what we are seeing, or second pixel, from the texel, if it is a distance kind of 20, then the delta distance what we are seeing, it will come as 0.6. Now if someone is a really high class mathematician, then he will compute the texel distance and pixel distance, and then so this is not the end. I am going to bring another one. Okay, so now we know that whatever the delta distance we want to kind of decrement from the texel manipulation. So now, so this delta distance would dependent upon the texel and pixel density and this triangle length. If this is the light source, then this is light vector L, and on this surface, this is the normal vector, and on the yellow surface, again red color what we see, that is the normal vector from the yellow surface. So L vector and N vector. So the angle, if it is big, the way we see on this table, then acne will be bigger, because the triangle will be longer. If triangle is longer, then interpixel length will be bigger. Okay, I can show like this. If triangle is big, then this is big. Now, if the angle is small, the way we see here, the triangle will be smaller. So, pixel will be at less distance from the texel. If that is the case, then anyway we see that acne distance is less and here it is more. So, the way this angle would change from the light source of the surface, then we have to multiply tan into the r cos dot L and n. So L dot n, if I do the dot, then I receive the cos theta, and if I do the r cos, then we receive the angle, and then tan of the tangent of that angle. So whatever the delta distance we are seeing, again we have to multiply by this factor. So if angle is 0, okay, so here it is 10 to 0, then nothing is required. There should not be any acne theoretically, but there is some angle, and if angle is 0, in some situations we won't see the shadow at all. And if angle is more, the way it is growing on this surface, then tan theta will grow. Tan theta grows with the angle. Okay, if it is 90, then it is 10 to, I believe it is infinite. So the acne will be very big. So we have to take care the inferences, we have to kind of take care the pixel and texel density and the angle between the light source, the L vector, and the normal of the surface. So this much if we compute, sit back nicely, then we are done. Okay, so I'm not going to do this much. So, okay, now I'm going to execute this again, and it is nearest, and this is how it is. I believe nothing has been changed. So that is the concept. So I'll have one output and then I'll compare with researched output. Okay, so this is the beginning one. We'll leave it as a beginning one. And now what we talked. So we'll go to the shader, and here So here I am going to comment it. So this is C code. So comment should be different. Minus 0.001. I believe that would be okay. And now if distance from the light, okay, so if the texture distance is less than shadow code minus 001. So we are subtracting so whatever we see from the second pass, the pixel depth, that depth will decrement so that it will come on the left side. So this is what is the discussion. So shadow coordinate in the second pass, whatever z we get, we will decrement with some value so that it would be on left side. Now if it is lesser, if right side is lesser, then it will be less than distance from the light. Okay, if right side is lesser, okay, then this would be false. If distance from the light, that is the texture, is less than this, it is not less than, because it is going on the left side, it would be brighter everywhere. Okay, so we'll try now. Okay, no one stops us in trying. Wow. Can we see the difference? I mean, anyone can see the difference. So is it different? Acne is gone completely. Now we can see pleasant shadow. Okay, so I am going to move the light and it will be on the left side. Now acne is growing because the angle is decreasing. We'll do the same thing. We'll do the same thing here and we'll try our luck. Acne is there, little bit it is there. Can we see? So in the worst scenario, what we see, acne is there, but in good scenario, acne is not there. Okay, but here in good scenario also, acne is there. So we improve. This I can guarantee. If angle is less, angle is so, we are failing in this scenario. So I have to use tangent, because if kind of angle is different, then kind of this triangle kind of its z component is different. I am not going to use that much. So okay, so I am going to increase this delta distance. So I consider this as less. So I am going to increase this. Okay, so this is how I am going to do now. Okay, so I'll make it 5. Okay, I am going to close it, Mr. Good, and I'll try again. Okay, so idea was better. Certainly it is better. Now at this angle also there is no acne, but I am not going to lose hope. There should be error. Life cannot be this easy. It's there at a very sharp angle, it is there. Can we see? Otherwise it's not there. Okay, so if someone calculates textile pixel density and tangent of the angle, then it will be completely alright, because in that fashion this hypothetical whatever we are changing now, it would change mathematically. Okay, so I can say 0.001. So I can say like 001. This is what we had taken initially, multiplied by 10 arc cos and then dot of ln n. Okay, and it would grow as per the scenario, but I don't want to do that much, so I'm going to increase it again. Okay, so we'll try. Okay, this would shift. If I increase, then this would shift. Okay, so that is the bottleneck. Okay, so this is transitioning acne, so it should be alright. So there is no acne. Okay, so this is how it is, and theory is theory, and practical is practical. Okay, what is the kind of next improvement that is required? We are looking at the center. We are looking at the center. Okay, we are not looking at the model. Okay, so that is the gap. Now, there is no, if I move the light source, now there is no shadow, but there should have been shadow, because light source is looking at the origin. There is no shadow, can we see? Because light source is seeing the origin, and when in that kind of frustum, GLU's perspective, this is not came. Now, the one other solution is that I have to increase this angle. It is 45. If I make 60 or 70, 75, then this sphere will come into the picture, then we can see. I mean, that is a problem. I mean, it should see the sphere, not the center. So that is the improvement that we can do. Okay, otherwise it is nice. Okay, so where are you, Mr. Sphere? Doesn't look good. Oh, it looks good. Okay, so kind of I can bind up. So we started with the shadowing in OpenGL, frame buffer, arc depth buffer, texture map, shadow, acne, and then adding bias. And then we see the light model, and there are two kind of camera. One is light and one is actual camera. And whatever we see from the light location, so that we can kind of through GLU look at, we can place the light at the center, and then we try to visualize how it would look. If that is the scenario, then we imagine kind of generating a texture map based upon the depth, and the raster would look like this. And then we go for actual frame buffer, and we attach a kind of a texture to the frame buffer, and in real sense we draw the raster with the depth wave. So this is what we saw. And then, so this raster is nothing but we can visualize through the images also. And then we came to conclusion that there is a texture generation phase and then actual phase. So in texture generation phase, we create the texture with the depth value, and since it is a texture, the coordinate is from 0 to 1. Top right is 1 and top bottom left is 0 as per the OpenGL analogy of a texture. And in the final pass from the light source, again we draw the kind of with the same frustum. For each pixel we draw kind of a texel coordinate. So texel coordinate, the x and y minus 1 to 1, we kind of do add bias and then we map it here in x and y. Then a z value we compare, and once we compare the z value, and then we kind of decide that it should be shadow or light, like all are light, but the area that is coming underneath the sphere, so these are coming as shadow. Okay, but we see the shadow acne because the discrete nature, digital nature of the image, where it had texels, texel density do not match with the pixel. Okay, and I do not match in a sense that they do not match physically, and this triangle, GL triangle, what we see, so this GL triangle, the depth of the GL triangle left to right, this also keeps changing if we change the angle between the light and the surface normal, so that we see. So the solution we came up that for a particular texel, whatever the area it covers in the pixel, so right side should be mapped to left side so that it would be bright, and whatever average we take, texel pixel density, the ratio, in that we have to multiply the L dot n and then that angle with the tangent so that it would keep changing. If that is the scenario, then we are not getting it. 2, we get it.